So the next topic for us, so now that we've tackled the product rule and the sum rule for counting, the next topic for us are going to be combinatorics, combinations and permutations. And we're going to start with permutations. So the way I like to think about permutations is a permutation is an arrangement. Okay, so a permutation specifically on a set of n elements says that, so a permutation is going to be the number of ways of ordering, the number of ways of arranging those elements in the set. Where you can only use one element once. So for example, if you have the set 1, 2, 3, it turns out that there's 6 permutations of that set. So there they are written out for us. So these are the 6 permutations. If you were to have a set with 4 elements in it, so let's jump to a new page here. If you were to have a set with 4 elements in it, so let's call that S, so 3, 4. How many ways are there to arrange all 4 elements? Well, you could arrange them 1, 2, 3, 4. You could arrange them 1, 2, 4, 3. You could arrange them 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, 2. You could arrange them, let's see how else. You could do 2, 1, 3, 4, 2, 1, 4, 3, 2, 3, 1, 4, 2, 3, 4, 1, 2, 4, 1, 3, 2, 4, 3, 1, and then we're halfway there. You could do 3, 1, 2, 4, 3, 1, 4, 2, 3, 2, 1, 4, oops, 3, 2, 1, 4, 3, 2, 4, 1, 3, 4, 1, 2, 3, 4, 2, 1. And then we could do, let's see, 4, 1, 2, 3, 4, 1, 3, 2, 4, 2, 1, 3, 4, 2, 3, 1, 4, 3, 1, 2, 4, 3, 2, 1. Okay, so these are the ways that you can arrange 4 objects. Okay, so if you have 4 objects, this is the ways that you can arrange them in that order. And it turns out that there's 24 such permutations. Okay, so 24. So if you were to have 1 element, there's only 1 way to do that. If you were to have 2 elements, there's 2 ways to do that. You could go, so if your S is just 1, 2, you could have, this is straightforward, 1, 2, or 2, 1. There's 2 ways to do that. If you have 3 elements, there's 6 ways to do it, as we saw above. If you have 4 elements, there's 24 ways to arrange those. So in general, the number of ways, the number of permutations on a set of n elements is going to be n times n minus 1 times n minus 2, all the way down to 1. And this, of course, is n factorial. That's what the factorial is defined as. So I'm assuming that we've seen the factorial in places before, but just in case we have not. N factorial, for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, so that turns out to be 120. 0 factorial, for good combinatorics reasons, is defined as 1. Okay, so that's called an empty product. It's the product of the empty set, so that's defined to be 1. If you were to have 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. So that's 720. But that's also 6 times 5 factorial. So that kind of observation that you can just take this 6 term, ignore it for a second, and what you're left with is 5 factorial, put it back, and you end up with 6 factorial is 6 times 5 factorial. Okay, so that observation will be very helpful as we go forward. So it turns out that there's n factorial permutations on a set of n elements. Now in R permutation, what that means is that you have n objects to start with, and what you're going to do is you're going to pick R of them to arrange in some order. So an R permutation is an ordered arrangement of R objects from a set of n objects. Okay, and so we'll denote the number of R permutations from a set of n objects as P of nr, sometimes said n permute R. Okay, so let's think about this for a second. In fact, let's look at example number 10. We have 10 books. We want to choose, I shouldn't use the word choose, which I'll explain in a second, but I want to arrange 3 of them. I'm going to pick 3 of them to arrange in a certain order. How many ways are there to do that? Well, we have 10 choices for the first book, 9 choices for the second book, and 8 choices for the third book. So it turns out that altogether there's 720 ways that you can arrange 3 books on a shelf given a set of 10 books to start with. Okay, this is 10 factorial divided by 7 factorial. If you think about what 10 factorial is, it's 10 times 9 times 8 times 7 factorial. And so you can take 10 factorial divided by 7 factorial, you'll end up with 10 times 9 times 8, which is 720. In general, the number of R permutations on a set of n objects is going to be, well, we'll do a similar count. You have n choices for the first object, n minus 1 for the second object, n minus 2 for the third object, all the way down to n minus r plus 1 for the rth object. And you can write this, if you like, as n factorial divided by n minus r factorial. Okay, so this is the formula that we're going to use for n permute r. Okay, so this is important enough. I want to put this in a little box here. Okay, so that's n permute r. That's our formula for it. Now, we're going to jump to combinations. Combinations are a little bit more involved. The idea here is a similar one, but it's a little bit different. And so to think about combinations, the way I like to think about this is as follows. So let's say that we had 3 people. So let's jump down to some scrap paper here. So let's say that we had, let's say that we had 3 people, Adam, Bonnie, and Carol. Okay, so we have Adam, Bonnie, and Carol, which I'll call A, B, and C. If we want to count the number of permutations, the number of ways to arrange them, say sitting at a table, say we had 3 spots at a table for them to go in, there would be 6 arrangements or 6 permutations, because you could put, you have 3 choices of who to put in the first spot, 2 choices of who to put in the second spot, 1 choice who to put in the final spot. Now, there's 6 arrangements, and that's fine. But let's think about how many ways. So let me write these out. We have AB, AC. Actually, what I said was ABC, ACB, BAC, BCA, and CAB, CBA. Okay, so that's fine. That's old news. Now, relatedly, if I just had 2 spots, but 3 people, how many ways are there to arrange those 3 people? Okay, so you have 3 people, you want to just arrange, you want to pick 2 of them and put them in some order. And it turns out that there's still 6 orders. There's still 6 ways to do that. And you can just calmly delete that third entry of each of the values. And there's the 3 different ways that you can arrange two people out of a set of 3 people. So again, it turns out that there's 6 ways here. So 6 arrangements. So in other words, what we just said is that 3 permute 2 is 6. Okay, so these are the 6 arrangements. Now, what I want to do instead, when we're talking about combinations, we don't care about the order in which they're arranged. We want to know how many ways are there to pick 2 people from a set of 3. So in other words, you can think about this as you start with 3 people. How many ways are there to pick a team of 2 people from that set of 3? And so what we're going to do is notice that Adam and Bonnie and Adam are the same team. So I'm going to cross off the Bonnie and Adam team. And likewise, Adam and Carol and Adam are the same team. And Bonnie and Carol and Bonnie are the same team. So it turns out that there's only 3 2-person teams that you can make of 3 people. And that's AB, AC, and BC. And that's because we don't care about the order that they're picked. We just care about who are the 2 people that are picked, regardless of the order, excuse me. So it turns out that there's 3. This second thing that we did where we were creating these 2-person teams is what's called a combination. Okay, so an R combination. An R combination refers to starting with a set of n objects or n whatever, in this case people. So starting with a set of n things, how many ways are there to choose a set of R of them? So in other words, how many ways are there to make an R person team, a team of R people, if you start with a group of n people? Okay, so these are called R combinations. We denote it n choose R, or actually how we denote it really is n choose R, like this. So these are called binomial coefficients for reasons that will be made clear soon. But the formula for this, it turns out, is going to be related to how we counted before. So I think it's actually easiest just to think about how many R permutations are there. And then given an R permutation, you're going to divide by the number of ways of rearranging that permutation. So for example, if you had a permutation of R people given a set of n people, then you would divide by R factorial, because given R people, there's R factorial ways of arranging them. So just to make that even more clear, what I want to do is I want to think about, let's say, P of 5, 3. I want to compute that. It turns out that this is going to be 60. So what I'm going to do is I'm going to start with the numbers 1 through 5. And then what I'm going to do is I'm going to think about all the ways that I can arrange 3 of those numbers. Okay, so we're going to start with 1, 2, 3, 4, 5. And then we're going to think about how many ways can we arrange 3 of the numbers. Okay, so this will take a second. I will edit out the pain here, but we're going to have the following ways. So we'll have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, 1, 2, 4, 1, 4, 2, 2, 1, 4, 2, 4, 1, 4, 1, 2, 4, 2, 1, 1, 2, 5, 1, 5, 2, 2, 1, 5, 2, 5, 1, 5, 1, 2, 5, 2, 1, 1, 3, 4. So that's going to be 1, 4, 3, 3, 1, 4, 3, 4, 1, 4, 1, 3, 4, 3, 1, 1, 3, 5. So that's going to be 1, 5, 3, 3, 1, 5, 3, 5, 1, 5, 1, 3, 5, 3, 1, 1, 3, 1, 4, 5. These are getting a little bit spread out, so let me move them just together just a little bit, and then I'll separate them with some columns here. Okay, just put in a little dividing line. Okay. And so what's next? We're going to have 1, 4, 5, and I think that'll be the last ones that have 1 in them. So 1, 4, 5, 1, 5, 4, 4, 1, 5, 4, 5, 1, 5, 1, 4, 5, 4, 1. Next we'll have, let's start with 2, 3, 4, 2, 4, 3, 3, 2, 4, 3, 4, 2, 4, 2, 3, 4, 3, 2. After that, we'll have, let's see, 2, 3, 5. So we'll have 2, 3, 5, 2, 5, 3, 3, 2, 5, 3, 5, 2, 5, 2, 3, 5, 3, 2. Okay, and then a few more. Let's see, we'll have 2, 3, 6, 2, 6, 3, 3, 2, 6. Nope, no 6s. Just kidding. Just kidding. 2, 4, 5, 2, 5, 4, 4, 2, 5, 4, 5, 2, 5, 2, 4, 5, 4, 2. Okay. Any more? Yeah, 3, 4, 5. That's the final one. 3, 4, 5. 3, 5, 4, 4, 3, 5, 4, 5, 3, 5, 3, 4, 5, 4, 3. Whew. Okay. So these are the number of arrangements that you can have. Okay, if we start with 5 objects and we want to arrange any 3 of them. Okay, so that's how we can do that. Now, that tells us that the number of 3 permutations on a set of 5 objects is 60. Okay, so that's how we calculate that. So there's 60 of them. Of course, there's 10 columns and 6 values in each column. So 60 objects total. So that's fine. Okay. Now, how many combinations can we make there? So let's think about what's 5 choose 3. Well, remember that with combinations, we don't care about the order that they're chosen. Okay, so we don't care about the order that these are chosen. In other words, we don't care about the order that they're written down. So if you think about that, it turns out that any value in this column are going to be the same. So there's, however you want to arrange the values 1, 2, and 3, that's only going to be one combination. And likewise, if you look at 1, 4, and 2, that's the same as 1, 2, and 4. And so all that's going to matter is the first value in each column. Okay, so those are going to be the ones that give us distinct grouping. So if we start with 5 objects and we want to choose any 3 of them, it turns out that there's 10 ways to do that. The reason why we divide by 6 is that 6 was the number of ways to arrange 3 objects. So given any 3 objects, say 1, 2, and 3, there were 6 ways to arrange those 3 objects. So we're going to divide by 6, in other words, divide by 3 factorial to get the proper count. So this is why 5 choose 3. So I'll start writing, since I've written it like this above, let me just copy it. So C of 5, 3, or 5 choose 3. I'll start writing it. I'm going to start writing it like that. Okay, that's 5 over 3 in parentheses. That's going to be 5 permute 3, which was 60, divided by 3 factorial. So that was 60 over 6, or 10. Okay, so this is the relationship between permutations and combinations. So let's go back up and let's fill in the details that we're missing. The number of R combinations is denoted as N choose R. Okay, and I'm going to again use this notation of N over R. So it's kind of looks like a fraction, except that line there is missing. So you just put an N over R in parentheses. That's called N choose R. And so it turns out that the formula for N choose R is going to be N permute R over R factorial. In other words, you can take the formula for N permute R and you can divide by R factorial again. So you end up with N factorial over N minus R factorial divided also by R factorial. Okay, and so this is going to be a good formula for us. Okay, so that'll be the formula for the number of R combinations on a set of N objects.